Today we will begin our discussion of Chapter 12 on combinatorics and probability. In particular, we'll cover Section 12.1 on combinatorics. Before we go any further, I want to remind you that if you're not already bringing your calculators to class, please do so from now on. You need to be following along with these calculations as we do them. It will really help you a lot, and you're doing yourself a disservice if you don't do so. Having said that, let's continue. So you think that you know how to count. Well, you probably do if you have a small number of items. For a small number of items, we can count just by making a list. For example, if I ask you how many possible outcomes are there if you roll a standard six-sided die, you can simply list them. 1, or 2, or 3, or 4, or 5, or 6. Those are all the possibilities for a standard six-sided die. Count them, and there are 6 possible outcomes. So yes, if you had in mind that as how to count, then yes, I would agree you do know how to count. But keep in mind that previous exercise is just one of the very simplest examples in a field called combinatorics. We'll spend lots of time using combinatoric strategies to find and list possible outcomes and how to count these outcomes. And they won't all be that simple. The previous exercise is one of the simplest examples of a field called combinatorics. We'll spend lots of time using combinatoric strategies to find and list possible outcomes and to count these outcomes. Let's look at another simple example. If an ordinary coin is flipped, how many possible outcomes are there, and what are they? Well, a coin, a standard coin at least, has a head and a tail side. So the possible outcomes, if you list them, are heads, maybe use an H for that, and tails, perhaps a T for that. So there are only 2 possible outcomes. Again, a simple list will suffice. How about this one? List and count the number of different outcomes possible when one letter is chosen from the word Tennessee. Again, we'll make a list. There's a T in Tennessee. There's more than one E in Tennessee. There's multiple N's in Tennessee, multiple S's. And if you mark all those out, you can see that the possible outcomes are T, E, N, and S. And if you count them, there are 4 possible outcomes, each of which is a letter. So again, we've made a list and we've counted. Just as before, I'll typically throw in various definitions as we need them, and I want to talk about the term experiment. For us, an experiment is an activity with an observable outcome. That's all it is. And the set of all possible outcomes of an experiment is called the sample space of the experiment. Every exercise we just did is an example of an experiment. Flipping a coin, rolling a die, choosing a letter from the word Tennessee, all of those things are experiments. They're activities with an observable outcome. Don't think that an experiment has to be done in a lab. An experiment is simply an activity with an observable outcome. And if we're talking about the sample space, if I go back to the example of the coin toss, the sample space is H for heads, T for tails. For the single six-sided die roll, the sample space are the numbers 1, 2, 3, 4, 5, and 6. And for the letters in the word Tennessee, it's the set containing T, E, N, and S. Those are the sample spaces for each of those experiments. Now, all of these experiments do have one other thing in common, in that they are called single-stage experiments. All that means is we just needed to do one thing. For example, if we're flipping the coin, we just need to flip a coin one time. Roll the die, just roll it once, in order to get the outcomes. That's a single stage experiment where you really only have to do one thing to get the sample space. Another definition, an event is one or more of the possible outcomes of an experiment. Flipping a coin and having a head show up would be an example of an event. Events are sets. So you see the set containing the capital H. That just means that the set contains the outcome of having a head show up when you flip the coin. Rolling a 5 when a die is tossed is an event. The event will be represented by the set containing the number 5. Choosing a T from the word Tennessee, it would be the set containing the letter T. That would be the event. Choosing a consonant from the word Tennessee. Well, there are two consonants in Tennessee. There's a T and there's an N. Those are all examples of events. It's just a set of one or more possible outcomes of some experiment. Keep in mind, though, I said that events were sets, but in particular, an event is a subset of the sample space. Remember, a subset is a set, but it's a particular set. An event is actually a subset of the sample space. It's some subset of the set of everything that could possibly happen in an experiment. However, unlike for a single-stage experiment, each outcome of a multi-stage experiment requires at least 2 steps. Single-stage experiment requires 1 step. A multi-stage experiment requires 2 or more steps. But because of the multiple stages, we often need additional strategies for finding the sample spaces because of the added complication of having multiple steps. For a 2-stage experiment, sometimes it is most efficient to make a table. We talked about making a list. 2-stage experiments lend themselves to tables. For example, if I ask you to find the sample space of all 2-digit numbers formed from the digits 1, 3, and 8, and ask you how many there are, a perfectly reasonable strategy would be to make a table. It's a 2-stage experiment because you're going to look at 2-digit numbers. So if you made a table, you might put 1, 3, and 8 as a heading for the rows and 1, 3, and 8 as a heading for the columns, and then look at the intersections of the row and columns, and that tells you the 2 digits. So where 1 and 1 intersect, you get 1, 1. Where 1 and 3 intersect, you get 1, 3, and so on. And when 8 and 8 intersect in the bottom right corner, you get 8, 8. And from that table, you can count and see that the possibilities for the sample space 11, 13, 18, 31, 33, 38, 81, 83, and 88. That's the sample space. To answer the question, how many, you simply count. 1, 2, 3, 4, 5, 6, 7, 8, 9. So there are 9 elements in the sample space. Creating a tree diagram is also a strategy, and in fact, it's probably a more general strategy than building a table. Typically, you're going to build a table when you have a 2-stage experiment. Tree diagram is useful even if there are 3 or 4 or more stages, and I'll show you what I mean. Suppose a true-false test consists of 10 questions. We want to draw a tree diagram to illustrate the number of ways to answer the first 3 questions. A tree diagram looks like this. It can spread horizontally or vertically. I've got one spreading horizontally, but it can certainly spread vertically. In this case, the tree diagram, the branches are the line segments, and the nodes have the possibilities. So on the first question, the answer is either true or false. So I have a node for true and a node for false. For question 2, though, if I've answered question 1 as being true, then the second question can either be true or false. And if I've answered the first question as being false, the second question can be either true or false. So you can see that the tree is branching. Those line segments are like the branches of the tree. It's a 3-question test. It would be one more set of branches. And so at each stage, each node has a true-false branch. That's the reason it's called a tree diagram. It sort of looks like the branches of a tree. This was a 10-question test, but they only ask about the number of ways to answer the first 3 questions. So because they only ask about the answer to the first 3 questions, we only go 3 levels in, which means this is a 3-stage experiment. Of course, if they had asked us to do all 10 questions, you can see very quickly how that tree diagram would get really complex. Because every stage, you double the number of possibilities. But in this case, we're only doing 3 questions. So now we want to count the number of ways to answer the first 3 questions. So it would probably be a good idea to list those number of ways. The tree diagram allows us to produce a list. And if you just go down every branch, you can see what happens. You can get TTT if you go along the first top branch. And as you keep branching off, you get TTT, TTF, TFT, TFF, FTT, FTF, FFT, and FFF. So the tree diagram allows you to explore every possible combination of T's and F's for a 3-question segment of that test. And now it's just a matter of counting, and you can see that the sample space has 1, 2, 3, 4, 5, 6, 7, 8 elements. So there are 8 ways to answer the first 3 questions of a true-false test. As long as the size of the sample space isn't too large, using these lists, tables, tree diagrams to find the sample space and then counting, which is what we've been doing, is in fact a reasonable way of finding out how many possible outcomes there are. However, as the number of possible outcomes gets larger, and if we're truly only interested in the size of the sample space, it really would be nice to have a procedure that doesn't force us to write out a really large sample space and then count. It turns out that in many cases such a procedure does exist, and it's based on a result called the counting principle. Maybe the best way to see this is by looking at an example. In fact, let's go back to the previous example involving those true-false test questions. Recall that we had a true-false test consisting of 10 questions, and we were trying to find out how many ways there are to answer the first 3 questions. And we did a tree diagram, and it turned out that there were 8 different ways. Let's look at this in a little more detail. For question 1, there were 2 possible answers, true or false. For question 2, there were also 2 possible answers, true or false. And for question 3, there were 2 possible answers, true or false. Now, think about this a minute. 2 times 2 times 2 is equal to 8. Is it simply a coincidence that we got 8, which is what we got earlier when we simply counted all the branches? We certainly haven't proven anything, but it turns out that this is more than a coincidence. It suggests a result which turns out to be the case. It's called the counting principle. The counting principle says a task composed of a series of stages in which the first stage can be done in A ways, the second in B ways, the third in C ways, and so on, can be done in A times B times C times and so on ways. In other words, you count how many ways each stage can be done, and you do that for each stage, and then you take the product. That's a very nice result and also a very useful result. Think of it this way. Because you're choosing answers to 3 questions, it's a 3-stage process. So you can say, okay, stage 1, you've got to figure out how many ways you can choose your answer for question 1, and it turns out to be 2, either true or false. Then you move on to stage 2. Stage 2 is the number of ways you can answer question 2. Well, again, it's only true or false, so that's another 2 ways. And stage 3, you need to count the number of ways to choose an answer to question 3. And since it's also true false, there are 2 ways. And by the counting principle, you take the product of those 3 counts, 1 for each stage. So you get 2 times 2 times 2, which is 8. Had we known that earlier, we could have avoided the tree diagram and gone directly to the answer 8. That's the nice thing about the counting principle. Or actually, something even nicer, it works just as well when the number of stages goes higher than 3, whereas a tree diagram could get unmanageable very quickly. So this counting principle is a very powerful tool in our toolbox. In any case, it matches, that 8 matches the same answer we got when we did a tree diagram, and it's no coincidence because of the counting principle. Let's try another. How many possible outcomes are there if we roll 3 ordinary dice? Well, think about it a minute. You're going to roll 3 dice, so this is a 3-stage experiment. Stage 1, you need to count the number of ways for die 1 to be rolled, number of outcomes you can have. Stage 2 will be the number of outcomes for die 2, and stage 3 will be the number of ways you can roll and get an outcome for die 3. And the counting principle says once you get each of those counts, you multiply them together. Well, with the true-false question, there's only 2 possibilities, but with an ordinary 6-sided die, there are 6 possibilities. But not just for the first die, there's also 6 for the second and 6 ways for the third one. And by the counting principle, we take 6 times 6 times 6, and we get 216. So there are 216 possible outcomes when you roll 3 ordinary 6-sided dice. And that problem would truly be difficult to do with the tree diagram. It would have 216 branches. Relatively unmanageable task. So you can sort of begin to see the power of the counting principle. Let's do another one. In horse racing, winning a trifecta means choosing the exact order of the first 3 horses crossing the finish line. If there are 8 horses racing, how many trifectas are possible, assuming there aren't any ties? Well, again, the trifecta consists of 3 horses crossing in some order, the first 3. So stage 1 is the number of ways you can assign a horse as being a first place winner. Stage 2 would be the number of ways you could choose a second place winner. And of course, the third stage would be the number of ways that you could have a third place winner. And by the counting principle, you would multiply those 3 counts together to get the total number of ways you could get a trifecta. So looking at the first stage, how many ways can you get a horse finishing first place? Well, there are 8 horses, so any of the 8 could theoretically win. However, if a horse wins first place, that horse can't also win second place, so that only leaves 7 horses that could possibly finish second. And using the same logic, if a horse wins first and a different horse wins second, neither of those 2 horses are available to also win third place, so there are only 6 horses left that could possibly finish in third place. So by the counting principle, there are 8 times 7 times 6, which is 336 possible trifectas. Again, you see the power of the counting principle. When you're doing these problems, there's a really important principle that you need to think about, and that is whether you're counting with replacement or without replacement. What do I mean by that? The idea is, do I have a previous choice available to choose in a later stage? For example, if I went back to that problem of rolling 3 dice, remember the calculation was 6 times 6 times 6. It was a 3-stage experiment, and it was 6 times 6 times 6 because each die row could be any one of 6 possibilities. In that sense, you can say that the number was replaced between stages. So if I roll the first die and get a 5, that 5 is still available for the second and third row. So in that sense, it's been replaced between stages. On the other hand, if I go back to the trifecta example with the horses, notice that it wasn't 8 times 8 times 8, it was 8 times 7 times 6. Because when a horse won at a certain stage, that horse was not available to win in a later stage. In that sense, the horse is not replaced between stages. So look at that and make sure you get the distinction. With a die roll, when you roll a die and get a certain number, that number is certainly available to be rolled again. So that's sort of with replacement. But with horses and placing in first, second, or third, a horse cannot place second if the horse has already been a first place winner, and cannot finish third if that horse has placed first or second. In that sense, the horse is not replaced between stages, and that is without replacement. Very important concept. Think about this, because if you don't understand that, you're probably going to have trouble with some of these counting principle problems. Let's look at this. A person reaches into a box with one red, one blue, and one green ball and randomly pulls out 3 balls, one at a time. How many different ways can this be done? Well, again, this is a 3-stage experiment because we're drawing out 3 balls one at a time. But keep in mind, the sequence of colors chosen will depend on whether the balls are returned to the box after each pick. So you've got a box that's got one red, one blue, and one green ball in it. So if I reach in and grab a ball and see that it's red and write down red, if I leave the ball out, my next draw is without replacement. But if I take that red ball, put it back in before I draw the second ball out, then that is with replacement. So you have to be very careful with these problems to know whether you're drawing with replacement or without replacement. This problem can be thought of either way. When it makes sense either way, you really have to say explicitly which case it is. So I'll do it for both cases. Suppose I say we're doing this with replacement. In other words, I'm going to reach into that box that has one red, one blue, and one green ball in it and pull out the balls one at a time with replacement. That means I draw out a ball, look at the color, put the ball back in, shake them up, and then draw a second time, look at the second ball, put it back in, again, shake them up, scramble them up, and then draw a third time. So if I'm drawing with replacement, my 3-stage experiment has a different count, because although they start off the same way, if I have 3 balls in this box, one red, one blue, and one green, I could get any 3 of them on the first draw. Now, if I'm drawing with replacement, that means after I look at the color of the first ball, I put it back in and shuffle them up and scramble them up and draw a second time. So I still have all 3 balls to choose from on the second draw. And that's also true of the third draw. If I'm drawing with replacement, the number of balls in the box never changes. It's always 3. So by the counting principle, I take those 3s and multiply them together and get a total of 27. So if I'm drawing with replacement, there are 27 different ways that I could get combinations of colors. It could be red, 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 blue, red, green, blue. If you figure out every one of them, it turns out to be 27 different ways. What's different about it if I do it without replacement? If I do it without replacement, the first draw is the same. I start off with 3 balls in that box, so there are 3 possibilities. But if I'm drawing without replacement, when I pull a ball out, it doesn't go back in, so there are only 2 balls left for the second draw. And after I've pulled 2 balls out of the box without replacing either of them, that leaves me only 1 ball in the box for the third draw. And by the counting principle, that would be 3 times 2 times 1, which is 6. So if I'm drawing with replacement, I have 27 different ways it can be done. If I'm drawing without replacement, there are only 6 ways. It's a very important distinction, and you need to think on this until you can see the difference and reliably handle the difference. Let's try another. How many 4-letter groups of letters can be formed from the letters A, B, C, and D if a letter can be used more than once? If you can use it more than once, that's like with replacement. You're drawing a letter, looking at it, and then putting it back in before you draw another letter. So that selection is with replacement. We're drawing out 4 letters, so this is a 4-stage experiment. The first stage, you're drawing from A, B, C, D. Think about those 4 letters being written on a piece of paper and shuffled around in a box, and you reach out and draw one. There are 4 letters you can draw. But if you draw with replacement, once you look at what letter it is, you put that slip of paper with that letter on it back in and shuffle them up again and draw again. So you still have 4 to choose from, and that's true for the 3rd draw and the 4th draw as well. So by the counting principle, there are 4 times 4 times 4 times 4, which is 256 different letter groups that can be formed if you do it with replacement. But what if you do it where a letter can only be used once? That means once you pull a letter out, you can't put it back in again. Well, this time you're drawing without replacement. So it starts off the same. There are 4 letters, but once you look at that letter, you don't put it back in, so there are only 3 left for the 2nd draw. There are only 2 left for the 3rd draw, and by the 4th draw, there's only 1 letter left. So by the counting principle, if you draw without replacement, you get 4 times 3 times 2 times 1, which is 24 different 4-letter groups. Again, if you're drawing without replacement. Look at those 2 things carefully and make sure you see the distinction. How about this? 2-digit natural numbers are formed with replacement from the digits 0 through 9. How many 2-digit odd numbers are possible? Okay, you have to think about this carefully. If you're choosing from the digits 0 through 9, you might want to write them out, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And you're making a 2-digit odd number. So I just put a space for the digit on the left and a space for the digit on the right. One thing to think about, though, when you write a 2-digit number, you generally don't write it with a leading 0. So you wouldn't call 1 0 1, you wouldn't call 5 0 5. So for that leftmost digit, or the first one in the list, there are really only 9 legitimate possibilities because you don't want that first position to have a 0 in it. If you're only choosing from the digits 1 through 9, there are 9 possibilities. And again, the reason I'm leaving off 0 is because I don't think of 0 1 as being a 2-digit number, or 0 7 as being a 2-digit number. So I don't want that leading digit to be a 0. Now the next digit, in order for the 2-digit number to be odd, the next digit has to be odd. Well, of the numbers above, there are 1, 3, 5, 7, 9. There are 5. 1, 3, 5, 7, 9. There are 5 choices that leave you with an odd number. And 5 times 9 is 45 by the counting principle. So this one was a little trickier because if you wanted it to be a true 2-digit number, you didn't want the 0 to appear in the first position, so you had to choose from 9 instead of 10. And for the second position, you wanted it to be odd, so you could only choose from the odd numbers, and there are only 5 odd numbers up there, 1, 3, 5, 7, and 9. A little different, but the same idea. So there are 45 possible 2-digit odd numbers. One thing you'll find out about this chapter is that you're going to have to become relatively comfortable with the cards in a standard 52 card deck. And the sooner you do it, the better you are. Standard deck has 52 cards, and I've spread them out here. There they are. There are several things about this deck that you need to know. First of all, there are 26 black cards and 26 red cards, because 26 plus 26 is 52. Half the cards are black, half the cards are red. Standard deck of cards, half the cards are black, half the cards are red. That's 26 and 26. Also, the cards are divided into 4 suits. The suits are clubs, which is the top row, and there are 13 of them. Spades, that's the second row from the top. Hearts, that's the third row from the top. And diamonds, that's the bottom row. So you've got to learn those symbols and what they mean. The symbol for clubs, the symbol for spades, the symbol for hearts, the symbol for diamonds. 13 clubs, 13 spades, 13 hearts, 13 diamonds. 13 times 4 is 52. Or 13 plus 13 plus 13 plus 13 is 52. So the deck has 52 cards, 26 black, 26 red, 13 clubs, 13 spades, 13 hearts, 13 diamonds. Those four things are called suits. Clubs and spades are black suits. Hearts and diamonds are red suits. There are also face cards, and the face cards, very simply, are the cards that have faces on them, and there are 12 of them. That J stands for Jack, that Q stands for Queen, and that K stands for King. There's a Jack, Queen, King of clubs. There's a Jack, Queen, King of spades. There's a Jack, Queen, King of hearts, and there's a Jack, Queen, King of diamonds. So there are 12 face cards. There are also different denominations, and starting from left to right, the cards with A on them are called aces, and in some sense you can think of those as ones. Then you have twos, threes, fours, fives, sixes, sevens, eights, nines, tens, and then the face cards, jacks, queens, and kings. So there are 4 aces, 4 twos, 4 threes, 4 fours, 4 fives, 4 sixes, 4 sevens, 4 eights, 4 nines, 4 tens, 4 jacks, 4 queens, and 4 kings. And if you add up all those fours, you get 52. That's what a deck of cards looks like.